Today we're on the chapter 15 packet and we're going to continue our talk about buffers on page 2. We're going to start off with what I call solution scenarios. There are 3 different solution scenarios that you can have. We've actually already learned in chapter 14 what to do with a strong, and we've learned what to do with a weak. So with a strong, remember, if you have a strong acid or strong base, the molarity of that strong acid or strong base will equal the molarity of the H plus or the OH minus. Don't forget, for a base like calcium hydroxide, which has 2 OHs, you'd have to double that molarity. Then if you have a weak acid, you would do an ice chart and set equal to Ka, or a weak base, you would do an ice chart set equal to Kb, and you must use molarity for an ice chart. Then in this chapter we just introduced what to do with a buffer. We learned that there's a buffer shortcut that takes the place of doing all of this calculation that we learned before with ice and Ka or Kb. You can just use the shortcut to replace the ice process and setting it equal to Ka or Kb, and you just do H plus equals Ka times A over B, or the base buffer shortcut is OH equals Kb times B over A, and we said you're allowed to use molarity or you're allowed to use moles for this. So these are, again, what we call the solution scenarios. It's like a beaker sitting there by itself. Now we're going to figure out what happens when you add something to a solution. The first thing you have to ask is, does it react? In other words, is it an acid plus a base that are not conjugates of one another? If the answer is no, they do not react, then just go to the correct solution scenario of being either a strong or a weak or a buffer. If the answer is yes, then you do stoichiometry in moles, like they do react, an acid and a base, they react. You do stoichiometry in moles, and then when you're done, you go back to your appropriate solution scenario. Okay, this process is going to be a pretty detailed process that we're going to practice a lot on. So let's move on to the first example. Let's suppose we have 1 liter of a solution that has 0.25 molar HCl and 0.5 molar acetic acid. So the first thing you have to ask, is there a reaction? So this is a strong acid, this is a weak acid. Will 2 acids react with one another? The answer is no, they will not. So since there is no reaction, then we're just going to go right to the correct solution scenario. The correct solution scenario is we have a strong acid and a weak acid. Whenever we have a strong and a weak, we really only care about the strong. So if we're going to draw a quick sketch of this, you'll see that you have a beaker here that has 1 liter of HCl, and you're also going to have HC2H3O2 in here. They don't react with one another. It's 1 liter. You have a molarity of 0.25 of this, and then 0.5 of this. So you know that that's going to be 0.25 molar H plus, which of course you'll also have 0.25 molar Cl minus, which we don't really care about right now. And this was a strong acid, but this is a weak acid, so you should do ice and Ka technically. But remember that when you do your X is going to be so insignificant, you're not going to worry about it. So that means that the H plus is still going to be 0.25. All right, so then when you take the negative log of this, you're going to find that the pH equals 0.60. So whenever you have a strong and a weak, a strong acid and a weak acid, you only care about the strong, because the weak one is not going to give you a significant amount of H plus. Okay, so there was no reaction in this example. So when we asked, does it react? The answer was no. So we went back to our solution scenarios. Now we're going to contrast with a yes. So I'll move this up here, and we'll take a look at this example. We have a beaker that has, first of all, a buffer in it. So let's draw a little picture of this. We have our beaker here. Oops. Inside this beaker, we have our acetic acid. And you know what? Just to make life easy, you can try this. Just write HA for the weak acid, and then you could write A minus for the conjugate base, and it just saves you a little bit of writing there. Okay, so we have a buffer. You have to understand what you even have in the beaker to begin with. You're starting off with a buffer. So this is 1 liter, and these are both 0.5 molar. So the acid is 0.5 molar of the buffer, and the base of the buffer is 0.5 molar in this beaker. Now look at what you're doing. You're adding 0.02 moles of H plus. So 0.020 moles of H plus are going into this buffer. So the first question, is there a reaction? The answer is yes, because whenever you have an acid going with a base that are not conjugates, they're going to react. So what's going to happen is the H plus is going to react with the conjugate base, the A minus, and that's going to produce the acetic acid. And what we're going to do here is stoich in moles. You have to do stoich in moles. So we're going to do an ice chart, ICE. We're going to start off with moles. Now this 0.5 molar was in 1 liter, so it was nice and easy, but you got to watch out, because if it's not 1 liter, it's not going to be the same numbers. So we had this much of that, and then we added of the strong acid the 0.020 moles. Oh man, sorry. Ugh, just messed that up. So this is a common mistake made by students and sometimes teachers. The HA starting amount was the 0.5. Okay, so this is the 0.5 of the HA, and then the acid that I added was the O2. So there we go. I did not do that on purpose, but it worked out. Now, you can see that the H plus is going to run out. So we're going to do minus 0.02 minus 0.02 plus 0.02. Now this is not ice. This is a limiting reagent, and so I should have written a final here. Sorry about that. All the common mistakes. So this is a 0. This is a 0.48, and this is a 0.52. Okay, again, these are moles. This is how much is left after you've added the H plus. So now the question is, what do I have? What solution scenario do I have? I have this HA, which is a weak acid. I still have A minus, which is the conjugate base, so I actually have a buffer. So now that I have a buffer, I'm going to use the buffer shortcut. Out of the solution scenarios, this is what I have left, a buffer. So I'm going to use the buffer shortcut for acid. So H plus equals Ka times A over B. The Ka, as we all know really well, is 1.8 10 to the minus 5th for acetic acid. Now the acid of the buffer is the 0.52. So I'm going to put 0.52 here, that's in moles. And then the base of the buffer is 0.48. So I'm going to put a 0.48 over here. And then when I'm all done, I'm going to find out that the H plus concentration is 2.010 to the minus 5th molar. And then when I take the negative log of that, I'm going to find out that the pH is 4.71. So let's take a look at what the delta pH was. Remember that in the other page of the packet that the original pH was 4.74. Okay, so I'm going to write this. Original pH is 4.74. That was from the buffer shortcut earlier in the notes. And now look, this one is 4.71. So that's only a difference of 0.03 pH units. Delta pH equals 0.03. So that's a very small change. And notice one more thing. We added an acid, and this pH started at 4.74, and now it went down to 4.71, which makes sense because we added an acid, so the pH went down. All right, you can guess what's coming up next. If we added an acid to the buffer, what would happen if we add a base to the buffer? So if you add a base to the buffer, it's the same type of calculation. All right, so what I'm going to do is I'm going to draw this all out. If you feel confident on this, you could just pause the video or do it while I'm talking. Either way, and then go to the end and see if you get the right answer. Okay, but I'm just going to talk through it now in case you want to hear one more time what to do. So here's my buffer. I have HA. I have A minus. It's 0.5 molar. I'm going to add in 0.020 moles of OH minus going into here. Remember that the original pH of this buffer was still 4.74 pH. So the first thing you do is ask yourself, is there a reaction when I put this base of OH minus into the buffer? The answer is yes, it will react. So because that is the case, I need to do stoich in moles. Now I'm going to write my stoich in moles. The OH minus that I added is going to find the acid portion of the buffer, and then it's going to make, I'll just write A minus, and is going to form water as well, but we're not really going to care about the water too much. We're going to do ICF, initial change final, as limiting reagents we used to do. So we write our 0.02 moles right here. We have our 0.5 of our acid, our 0.5 of our conjugate base, and we don't really care about the water. Now with limiting reagents, we're going to find out that the OH runs out. We're going to only use 0.02 of the acid. We're going to make 0.02 of the conjugate base. So when I'm all done, I have no more hydroxide. I have 0.48 moles of the weak acid, 0.52 moles of the conjugate base. And then I do my solution scenario and ask myself, what do I have now? A stronger, a weaker, a buffer? And I have a buffer. So because I know I have a buffer because I have a weak acid and its conjugate base. So I do the buffer shortcut, which is going to be, I could still do the H plus. You could go to the OH minus if you like, but I'll just do the H plus, equals Ka times A over B. Our Ka is 1.8 10 to the minus fifth. Our acid is the HA, which is this, 0.48. That's moles, divided by the base, which is the 0.52. And when you do the math for that, you're going to get a pH of 1.7. I'm sorry, not a pH, but a H plus of 1.7 10 to the minus fifth molar. And then when you negative log that, you're going to find out that the pH is 4.78. Again, that's only a delta pH of 0.04 off of our original 4.72. And look, this made sense because this went up because we added a base. So because we added a base, the pH of 4.74 went up only by 0.04 units, whereas the original problem I had up here, this pH went down by 0.03 because we added an acid. One last point, you'll notice that the delta pH for this one was 0.03. If I move this over a little bit. And this one over here was 0.04. So it's interesting that they're different, even though there was the same amount of 0.02 and 0.02. And what we're going to notice is that this is already an acid buffer. So if it's an acid buffer and you add an acid to it, the change is not as great. However, if you add a base to an acid buffer, it will change it a slight bit more.